In this lesson, we're going to learn more about covalent bonds and how they're related to the quantum mechanical picture of orbitals. Specifically, we're going to reconcile the picture of atomic orbital theory with the VSEPR theory. Recall that when we talk about covalent bonds, we talk about atoms sharing electrons between them. When we used VSEPR theory to build molecules, we called these shared electrons bonding pairs of electrons, and we used the number of bonding and lone pair electrons to determine the molecular geometry. We know that for the most part, the molecular geometries that VSEPR predicts are accurate, because we can measure the exact geometry of these molecules. VSEPR doesn't tell us anything about where those electrons are likely to be located, only that they are shared between the two atoms. So what exactly does it mean for electrons to be shared? In front of you are two hydrogen 1s atomic orbitals. In atomic orbital theory, we learned that these isosurfaces represent the surface within which there is a 99% probability of finding the electron. In other words, isosurfaces are a good map of where it is likely to find the hydrogen's only electron. We can also look at the probability of finding the electron anywhere in space using a dot diagram like the one in front of you. This picture of the hydrogen 1s orbital is helpful because it shows us the regions where it's most likely to find the electron. Here is the area where the dots are the largest and brightest. Take a look inside the orbitals to scan the probability. This picture of electrons is also helpful when we are thinking about bonding between atoms. Sharing of electrons between atoms in a molecule only occurs when there is overlap in the probability of finding the electrons between the two atoms. Bringing the hydrogen atoms closer together, we can see that these high probability regions overlap at a specific distance. In this case, when we bring the two hydrogen 1s orbitals close enough together such that there is a significant overlap in the probability of finding the electron, they form a bond. This is the ball and stick model for molecular hydrogen, H2. The two 1s orbitals participated in the formation of the bond between the two hydrogen atoms. This example illustrates how atomic orbitals are combined between atoms to share electrons. Let's look at another example to see where this breaks down. In front of you are the isosurfaces for carbon and hydrogen, as well as the molecular model for methane. We know from experiments that methane has a tetrahedral arrangement of hydrogen around the carbon atoms. The atomic orbitals of carbon which are available to form bonds are the 2s, 2px, and 2pz atomic orbitals. We can try and create methane by overlapping the hydrogen 1s orbitals with the valence orbitals on carbon. The animation in front of you is trying to overlap the hydrogen and carbon orbitals in a way that will result in the known tetrahedral geometry. We can see that despite your best efforts, it isn't possible to overlap the orbitals in a way that will result in a tetrahedral molecular geometry. So, how do we reconcile the picture of orbitals with the molecular geometries we know are correct from VSEPR theory? Head to the next chapter to find out. So, how exactly do we rectify the differences between the orientation of atomic orbitals and the geometries of molecules we know are correct? We can figure out the answer if we take another look at the dot diagram for the carbon atomic orbitals again. Looking at the dot diagram for the carbon atomic orbitals, we can see that the 2s and 2p orbitals have common overlap of the highest probability regions. This looks like a thin spherical shell where the highest probability of finding the electron is shared between the 2s and 2p orbitals. Take a closer look to verify for yourself. Just like in forming bonds when atomic orbitals overlap significantly, they can hybridize to form new orbitals. Hybrid orbitals are combinations of atomic orbitals and can occur in specific atoms where the atomic orbital's probability distributions overlap significantly. Let's learn a bit more about the rules which govern hybrid orbitals. This is the hybridizer. We're going to use it to learn the rules governing the formation of hybrid orbitals and what hybrid orbitals look like. The first rule is that we create the same number of hybrid orbitals as the number of atomic orbitals which are used. Let's look at an example in the next section. Go ahead and grab a 2s and a 2p orbital from the orbital palette and place them in the hybridizer. Once you've placed the orbitals in the hybridizer, hit the green button to transform them into their hybrid orbitals. Great job! You just created the sp hybrid orbitals. You can see that combining an s and a p orbital resulted in two sp orbitals in a linear geometry. 2 orbitals in, 2 orbitals out. Take a look at the hybrid orbitals. You'll notice that they have a different shape than the s and p orbitals which created them. You might have noticed that the way we name hybrid orbitals is not the most creative. The names of hybrid orbitals are designed to tell us exactly which atomic orbitals were used. In the last section, you made sp hybrid orbitals. Now let's make sp2 hybrid orbitals. Using the orbitals available in the palette, select the correct orbitals to create an sp2 hybrid orbital. Great job! You figured out the naming convention. The sp2 hybrid orbital results from combining an s orbital and 2 p orbitals. Whenever you see an exponent in the name of a hybrid orbital, it's indicating the number of that type of atomic orbital which was used. Looking at the sp2 hybrid orbitals, we can see that the first rule was obeyed. 3 orbitals in yields 3 orbitals out. We can also see that these 3 orbitals are arranged just as we would expect from Vesper theory. Spread as far away as possible. Go ahead and pick up the sp2 orbitals to take a closer look. Can you recall the name for the electronic geometry which corresponds to the geometry of sp2 orbitals in front of you? Select the correct answer from the options on the console. Let's look at a couple of other examples. Go ahead and use the hybridizer to create sp3 hybrid orbitals. These are sp3 hybrid orbitals. They're arranged in a tetrahedral geometry. Do you remember trying to build methane earlier? In methane, sp3 hybrid orbitals are formed, which give the molecule its tetrahedral shape. We'll learn more about that in an upcoming chapter. For now, go ahead and take a closer look at the sp3 hybrid orbitals. You may have noticed the d orbital sitting in the palette this entire time. In some atoms, d orbitals can also hybridize with s and p orbitals to form hybrid orbitals. Let's take a look at what happens when we make sp3d hybrid orbitals. Go ahead and do this now. Feel free to use the hybridizer to try and create any of the hybrid orbitals we've talked about so far. There's one last hybrid orbital we haven't talked about. You can move on to the next section after you've made it. I'll give you a hint. It has an octahedral geometry and so will require you to combine 6 atomic orbitals. In the last chapter, you probably noticed that the geometries of the hybrid orbitals which result from combining the atomic orbitals suspiciously resemble the geometries of molecules from VSEPR. Well, this is no accident. The concept of hybrid orbitals was developed to rectify the discrepancy between VSEPR and atomic orbital theory. In this chapter, we're going to build molecules using the hybrid orbitals we just learned about. We're going to start with the example from the very beginning of this lesson, methane. Go ahead and grab the hydrogen atoms and place them to create overlap between the 1s orbital and the sp3 orbital. You can see the sp3 hybrid orbital surrounding the central carbon atom. Now we can see that using hybrid orbitals, we are able to build methane with the correct tetrahedral geometry. For the rest of the lesson, we'll represent all terminal atoms as spheres for simplicity. In a future lesson, we'll explore more about what orbitals are involved in bonding for terminal atoms. The first step in building a molecule using hybrid orbitals is to determine which hybrid orbitals are needed. We do this in the same way that we determine the geometry in the VSEPR lesson. We sum the number of atoms and lone pair electrons around the central atom to determine the steric number. Let's look at beryllium difluoride as an example. You can see the Lewis diagram for beryllium difluoride on the tablet. Counting the number of atoms and lone pair electrons around the beryllium atom, we have a steric number of 2. This will result in a linear geometry. Can you recall which hybrid orbital had a linear geometry from the last chapter? For molecules with a linear electronic geometry or a steric number of 2, we'll need sp hybrid orbitals. Using the molecule builder, go ahead and create the molecular model for beryllium difluoride now. Awesome! This is the model for beryllium difluoride with the bonds formed using hybrid orbitals. The type of hybrid orbitals we use is related directly to the steric number, and the steric number is equal to the number of hybrid orbitals. The steric number for sp orbitals is 2. For sp2 orbitals, the steric number is 3, and for sp3 hybrid orbitals, the steric number is 4. Let's look at one more example. Looking at the tablet, you can see the Lewis diagram for tin chloride. From the options in front of you, what type of hybrid orbital will you need to build tin chloride? Now go ahead and build the tin chloride molecular geometry by placing the chlorine atoms. Great job! In this lesson, we aren't worried about the lone pair electrons, but they live in the sp2 hybrid orbital, which is not participating in bonding. Hybrid orbitals can contain both bonding electrons and lone pair electrons. Let's look at a couple of examples for molecules with large steric numbers. On your tablet, you'll see the Lewis diagram for phosphorus chloride. Using the hybridizer, go ahead and create the correct hybrid orbital you'll need. Now that we have the right hybrid orbitals, go ahead and build phosphorus chloride. We can see that the trend continued. The steric number is equal to the number of hybrid orbitals. In this case, sp3d hybrids have 5 orbitals and produce a trigonal bipyramidal geometry. Let's build one last example. On your tablet, you can see the Lewis structure for xenon tetrafluoride. Recalling what we know about the relationship between the steric number and the type of hybrid orbitals, create the correct hybrid orbital needed to build xenon tetrafluoride. Great work! We need sp3d2 hybrid orbitals to create xenon tetrafluoride, which has a steric number of 6. Now go ahead and build xenon tetrafluoride. Remember that we want to minimize the interaction between lone pairs when placing the fluorine atoms. We're almost done with this lesson. Before we let you go, let's spend a moment talking about organic molecules. Hybrid orbitals are very important to the geometry of organic compounds. The geometry of organic molecules strongly determines how they react. Here we see the ball and stick model for propane, C3H8. When drawing carbon-containing molecules, we often draw them with the zigzag along the carbon backbone. Using the available carbon and hydrogen atoms, can you build propane? Great job! You just saw how sp3 orbitals are used in building hydrocarbon molecules. Hybrid orbitals are interesting because the same atom can form different hybrid orbitals depending upon its environment. We'll see how this works for carbon in the next section. Let's build ethene to illustrate this example. Given the Lewis structure on the tablet for ethene, and recalling that the steric number is equal to the number of hybrid orbitals, use the hybridizer to build the correct hybrid orbitals needed to construct ethene. Great work! We need sp2 orbitals to build ethene, as each carbon atom in this molecule has a steric number. Let's build ethene to illustrate this example. Given the Lewis structure on the tablet for ethene, and recalling that the steric number is equal to the number of hybrid orbitals, use the hybridizer to build the correct hybrid orbitals needed to construct ethene. Great work! We need sp2 orbitals to build ethene, as each carbon atom in this molecule has a steric number of 3. Using the ball and stick model as a reference, can you build the ethene molecule using 2 carbons and 4 hydrogens? We're going to ignore the orbitals which form the double bond for this exercise. Interestingly, in this case, the carbon atoms adopt an sp2 hybridization to form the molecule. This results in a slightly different bond angle between the carbons and hydrogens. Let's look at one last example. Let's build ethene, which is 2 carbons connected via a triple bond. Here, the steric number is 2 for carbon, meaning we're going to use sp orbitals to form bonds. Go ahead and build ethene now. Again, we will ignore the orbitals which form the double and triple bonds for this exercise. Great work! You've finished the lesson. Feel free to use the hybridizer if you want to create any more hybrid orbitals and take a closer look at them. You can also go back to any chapter using the table of contents if you'd like to practice some more.